time domain expression for this IL for this second order circuits. The parameter has been given here, and we know the initial capacitor voltage is 50 volts. So the initial voltage V0 is 50 volts, actually across all the components, right? They are all parallel. And we also know that the initial current, this IL0 is 1 amp. Okay, this is another one. And we know this is 25 millihenry. We know the resistor is 12.5 omega. Yeah, that's pretty much what we have now. And to calculate this, again, we want to find out alpha, we want to find out omega 0. So we want to tell which one is this. Okay, and then after you identify the type of damping, then you can just use this equation. For example, if this one is a underdamped situation, then this is the final result you want to have. Okay, but there are some parameters you don't know, like a B1 and a B2. So you want to give initial condition for this one, and you also want to use this one. So two equations give you for this two unknown can be solved, and then you're going to plug everything into this one. All right, so that's the whole process. Let's do it step by step. Okay, first, omega 0 is always the same, but for the parallel, the alpha is look like this. So it's equal to 1 over 2 RC. Everything is known. Then you will find this one is 640 radians per second. For omega 0 is 1 over LC square root. And you will get this one is 800. And this time is alpha square is smaller than omega naught square, so is underdamped. Okay, so it's underdamped situation. So for the underdamped situation, there is omega d. Okay, so we need to calculate this omega d equals to the equation is over here. Is 800 square minus 640 square root. You got this 480. Okay, and you can see there is another thing we don't know is the final value. In this case is current, so we are looking for the current inductor final, or we write like this, right, infinite. So when the circuit reaches steady state, time is infinite, so the inductor become a short circuit. We did this so many times, so all the current will flow here through that. So finally this one gonna be 2 amp. All right, so we got a lot of information, and then we gonna write this IT equation, and when t equal to 0, so we're gonna use this two initial condition. Okay, so this we are looking for L0 is actually equals to this IL infinite or final plus. So we don't need to copy everything here, because if you plug this t equal to 0 in, this term is gone, right? This term is gone. So what you got is, and this term is also become a 1. This term become a 0. So this term becomes a 1 as well. So what you got is actually just a final value plus a B1. Okay. We want to use a B1 not here just to represent it's a bit different B1 compared to without this final value. but it's not that important. You just know this is a number, sorry, a variable. Okay, so what's the initial value for I current? It has been given. Okay, it has been given. So this equation just becomes 1 amp equals to 2 amp plus a B1 naught. So B1 naught just equals to a -1. Okay, no drama. And for there is a B2, okay, there is a B2 there, so we need to borrow this one to do that. So you don't need to worry too much about that. So the for the long one, we can simplify that very easily as well. So this dx, so we're talking about IL, right? T, we just plus t equal to 0 in dt. So this one gonna be simplified. So the whole term is gone because the sine 0 is 0. This one become a 1. This become a 1. This become a 1. This whole thing is gone. This become a 1. Okay, so this term is gone. So in the end, we always get this negative alpha B1 naught plus omega d B2 naught for this under damped situation. Okay, so this is a much easier. Now the challenge part is how much is this? Okay, di dt. What is a di dt? So if you're familiar with the definition of the capacitor, the inductor, so the voltage of the across the inductor is actually equals to L dIL dt. Okay, so di dt is just di dt actually just equals to VL over L. Okay, and we are talking about initial initial voltage, right? This is the initial condition. So initial voltage across the capacitor is just 50. Okay, so this one equals to 50 divided by L. L is 25 multiplied 10 to the order of -3. All right, and we already know alpha. We already know alpha is 640, and we already know B1, which is -1, and we're gonna plus omega d. We know that as well. B2 naught is the only thing we don't know, and equals to this thing, right? Then we can find out this B2 equals to 2.83. All right. So far we got everything. Okay. We're just gonna plug everything into this equation for xt. Okay. Gonna use this one. So let me move just a little bit. So the final result, ILT equals to final value, which is 2, and B1 is -1, so minus e to the order of -640, that omega d, what was that? Yeah, that's this one, right? Alpha, sorry, 640 is alpha, and multiply with cosine. This is omega d for AT t, and plus B2, right? Plus 2.83 e to the order of -40 for 640, and multiply with a sine for ATT. Okay, that's it.